Bismillah ar-Rahman ar-Rahim. This video is about Minkowski convex body theorem. We have a lattice in the n-dimensional Euclidean space. We have vectors b1 all the way to bn. Those are linearly independent vectors. The lattice is the collection or the set of points in the n-dimensional space that can be written as integer combinations of those vectors. So a lattice point is an integer m1 times the vector b1 plus an integer m2 times the vector b2 all the way to mn times vector bn. All points that are integer combinations of those linearly independent vectors are part of this lattice. The vectors can be collected in one matrix. In this case, the matrix will be a square n by n matrix that is invertible because those vectors are linearly independent. This is an example for a lattice in 2D. So here one vector, so this is b1 is equal to 1 and 0. And then there is another vector here, b2, and b2 is 1/2 and square root 3 over 2. The 2 by 2 matrix B is the matrix with elements 1, 0, 1/2 square root 3 over 2. What is the fundamental cell of a lattice? It is the points in the n-dimensional space that can be written as matrix B times theta. So this is a linear combination of the columns of matrix B. But the components of vector theta must be non-negative and they must be strictly less than 1. So here b theta is a summation I from 1 to n, and then we have bi, that's vector bi, and it is multiplied by theta I. This is this linear combination. Theta I is a number that is greater than or equal to 0, but it must be less than 1. The collection of all those points is called the fundamental cell of the lattice. In our example here, the fundamental cell is this parallelogram. These are the points that can be written as a linear combination of the basis vectors, such that those coefficients are non-negative and are strictly less than 1. To be exact, note that the fundamental cell includes the parallelogram and this edge, but there are two edges that are excluded. This one here, this edge is excluded, and this one is excluded. And the reason for this, that those points will require that theta is equal to 1, and all thetas are strictly less than 1. If we take the elements of b theta and add to mz, where z is a point in the lattice, then we have the fundamental cell shifted. So we can choose this point here as z, and then we can shift the fundamental cell to this point. The collection of translated fundamental cells partitions the n-dimensional space. What does this mean? It means that any general vector in the n-dimensional space can be written as the sum of two terms. One of them is a lattice point, and the other one is a linear combination that looks like this, a linear combination of the basis vectors with coefficients that are greater than or equal to 0 and strictly less than 1. To show this, let's take vector x. It's a general vector in the n-dimensional space. It is not necessarily part of the lattice. Now, those n vectors are linearly independent, so they can act as a basis for Rn. I can take vector x and write it as a linear combination of those n vectors. But those xi's will be real numbers. Now I can take each xi and write it as the floor of xi. The floor of xi is the greatest integer that is less than or equal to xi. So the floor of 2.7 is equal to 2. The floor of 13 is equal to 13. The floor of minus 1.2 is equal to minus 2, and so forth. Plus the difference between xi minus the floor of xi. That's the fractional part of xi. Typically, it is denoted like this. And I can split this sum into two sums. In the first one, I take the floor of those coefficients. All those guys are integers. So if we look at the first sum, it is an integer combination of the basis vectors from b1 to bn. By definition, this summation here, this integer combination, is part of our lattice. This is a vector in the lattice. And then what is the other term? The other term will have coefficients that are xi minus its floor. Xi minus its floor. This is 0 if xi itself happens to be an integer. And if xi is not an integer, this will be a number strictly between 0 and 1. So the difference between xi and its floor is a non-negative number that is strictly less than 1. So this summation here can be written as B, matrix B times vector theta, with components that are non-negative but strictly less than 1. Indeed, any vector in the n-dimensional space can be written as the sum of a vector in the lattice plus a vector in the form of b times theta, or summation of I from 1 to n, theta I bi, where theta I is greater than or equal to 0, strictly less than 1. The representation of x using vectors in the lattice lambda is a unique representation. Suppose that a general vector x in the n-dimensional space is equal to alpha 1 plus gamma 1. So alpha 1 is the vector that is in the lattice, and gamma 1 is a vector that looks like d theta. And also, it can be written as alpha 2 plus gamma 2. Suppose that x can be written as summation I from 1 to n, mi, bi, and those are integers, plus summation I from 1 to n, theta I, bi. And also, x can be written as summation I from 1 to n, mi tilde, again, those are integers, bi, plus summation I from 1 to n, theta I tilde bi. Suppose that these two, this and this, are representations of x using the lattice big lambda. Now, let's move all terms to one side. So if this is equal to this, then we have a summation I from 1 to n, and then we have the vectors bi. Now, each vector we have here multiplied by mi minus mi tilde plus theta I minus theta I tilde, and this is equal to the O0 vector in n-dimensional space. Now, the b vectors are linearly independent, so a linear combination of them to be equal to the O0 vector, it must be the case that each coefficient here is exactly equal to 0. Let's examine the coefficient multiplied by bi. Now, this is an integer. The difference between two integers is an integer. Theta I minus theta I tilde. Now, theta I is greater than or equal to 0, strictly less than 1. Theta I tilde is the same thing. So minus theta I tilde is strictly greater than minus 1 and is less than or equal to 0. Adding these two inequalities, theta I minus theta I tilde is strictly less than 1 and is strictly greater than minus 1. So this is a number that lives in the open interval from minus 1 to 1. Because the b's are linearly independent, and this linear combination of the vectors is the O0 vector, then we must have that the coefficients are equal to 0. So each coefficient is 0. But what is each coefficient? Each coefficient is an integer plus a real number between minus 1 and 1. How can this be 0? It must be the case that theta I minus theta I tilde, this must be an integer. For the coefficient to be equal to 0, then theta I minus theta I tilde must be an integer, because we cannot have an integer plus a number that is not an integer and then get a 0. So theta I minus theta I tilde must be an integer. But theta I minus theta I tilde, if it's an integer, it can only have one possible value, which is 0, because this is a number strictly between minus 1 and 1. So theta I minus theta I tilde is exactly equal to 0, which means that theta I tilde is equal to theta I for every I from 1 to n. Now, if these two guys are the same, then we are left with the integer mi minus mi tilde. This must be 0. Mi is equal to mi tilde. If x has two representations, they are exactly the same. We have shown that the coefficients must be exactly the same. Before proceeding to Minkowski theorem, let's prove this result. We have C, a non-empty subset of the n-dimensional Euclidean space. The Lebesgue measure of C, or the volume of C, is strictly greater than lambda. What is lambda? Lambda is the Lebesgue measure or volume of the fundamental cell. In 2D, the volume or Lebesgue measure is the area. So now we are talking about a non-empty subset of R2, and it has an area that is strictly greater than the area of the fundamental cell. Consider CZ. What is CZ? It is C, this subset of Rn, with a Lebesgue measure strictly greater than the Lebesgue measure of the fundamental cell. CZ is C, and then we intersect C with the fundamental cell, but translated by Z. C is the disjoint union of those CZ sets. As an example, what if we take Z to be this point? So this is the translated fundamental cell. What is the intersection between this and our set C? Well, it's empty. No problem. Now take Z to be this point. Here is the translated fundamental cell. Now there is an intersection between C and this translated fundamental cell. So CZ for this Z here will be this part. Now take Z to be this point. Here is the translated fundamental cell. And there is an intersection between C and this translated fundamental cell. And for this Z here, this is CZ. C is the union over CZ, where Z is a point in the lattice. CZ It is obtained by intersecting C with a fundamental cell that is translated by Z. Those sets here partition C into disjoint sets. In our example, C is partitioned into 5 non-empty sets. 1, 2, 3, 4, and 5. All the other intersections are empty. The volume of C is the sum of those volumes. So volume of C is the summation over Z in the lattice big lambda of the volume of CZ. Now take each CZ and translate it by minus Z. What does this mean? If I take this translated fundamental cell and it contains this part from set C, this is CZ, where Z is this point here. Now we subtract Z. Specifically, we translate this so that this point comes here to the origin. And so this part here will come here. And we will do this for every CZ. Sets CZ minus Z now are all moved to the fundamental cell, like this. The volume of the union of those sets CZ minus Z is less than or equal to lambda. Now they are translated and they are contained within the fundamental cell. But the sum of their volumes is the volume of C, our original set. And here we are studying a non-empty subset of Rn with a volume that is strictly greater than lambda. We have 2 points now. The first is that the sum of the volumes is strictly greater than lambda, but at the same time, the volume of the union is less than or equal to lambda. Then we must have intersection. To be exact, there are at least 2 intersecting sets. Let's say CZ0 minus Z0 and CZ1 minus Z1. Because our starting set C has a volume strictly larger than the volume of the fundamental cell, then if we do this game of partitioning C using the lattice and then bringing the parts to the fundamental cell, it must happen that there are 2 of those sets that are intersecting, because the volume of the union is strictly less than the sum of the volumes. Since there is an intersection, then there is a point Y that is in this set and that is also in this set. This means that the set CZ0, this set, it contains a point x0, which can be written as y plus z0. And CZ1 contains a point, let's call it x1, which is y plus z1. So that when we do a translation, this x1 will go to y and x0 will go to y. So there must be an x0 in CZ0, and CZ0 is contained in C. And this x0 is y plus z0. There is also an x1 living in CZ1, which is part of the set C. So there is an x1 in C that is y plus z1. What if we take the difference? x0 minus x1 is z0 minus z1. So x0 is a point in C. x1 is a point in C. Their difference is in the form of z0 minus z1. z0 is a point in the lattice. It's an integer combination of the b vectors b1 to bn. z1 is also a point in the lattice. The difference between 2 points in the lattice is a point in the lattice, right? So if z0 is summation vectors bi, I from 1 to n, and then we have coefficients, integer coefficients, let's say alpha I bar. z1 is also in the lattice, so it is summation I from 1 to n bi, let's say alpha I tilde, and those are integers. If we subtract, we get an integer combination of vectors b1 to bn. The difference between 2 points in the lattice is also a point in the lattice. So what is our result? Our result is that there must be 2 points, 2 vectors in the n-dimensional space. These 2 points belong to the set C. It's not an arbitrary set. It's a non-empty subset of Rn with a volume, with a Lebesgue measure that is strictly greater than the volume of the fundamental cell. There must be these 2 points such that their difference belongs to the lattice. Their difference can be written as an integer combination of the vectors from b1 to bn. Now to Minkowski theorem. We have non-empty S, which is a subset of Rn. S is symmetric, convex. Its volume is strictly greater than 2 to the power n times lambda, where lambda is the volume of the fundamental cell. Symmetric means that if Z is in S, then minus Z is also in S. If we have a point or vector Z is in the set S, then minus Z is also in the set S. Convex means that if Z1 and Z2 are in S, then for every eta between 0 and 1, eta Z1 plus 1 minus eta Z2 is also in S. So this is a convex combination of Z1 and Z2. This means that if there are 2 points in the set, then all the points on the line segment connecting Z1 and Z2 will also be in the set S. Let's define the set S prime. It's S over 2. What do we mean by S over 2? The set S prime is the set of vectors that are n-dimensional, that are obtained from the vectors of set S by dividing each component by 1/2. There is a bijective map between S prime and S. Every vector in S, if multiplied by 1/2, we get a vector in S prime. Every vector in S prime, if multiplied by 2, we get a vector in S. Because each component or coordinate is multiplied by 1/2, then the volume of S prime is 1/2 times 1/2 n times the volume of S. So the volume of S prime is the volume of S divided by 2 to the power n. But the volume of S, it is given that it is strictly greater than 2 to the power n times lambda. So the volume of S prime is strictly greater than 2 to the n times lambda divided by 2 to the n. So the volume of S prime is strictly greater than lambda. So we can apply our previous result. If we have a set with a volume that is strictly greater than the volume of the fundamental cell, then there are 2 points, 2 vectors in this set. In our case here, it will be S prime. And here, let's emphasize that these 2 vectors are distinct. There will be 2 vectors such that their difference is in the lattice. Their difference belongs to the lattice. Their difference can be written as an integer combination of the vectors from B1 to Bn. Now, the vector Q0, it is some vector Y0 in S that is divided by 2. And the vector Q1 is some vector Y1 that is in S and that is divided by 2. Recall that S has these 2 properties. It is symmetric and it is convex. Because S is symmetric, if Y1 is in S, then minus Y1 is in S. Since S is convex, you have Y0 is in S, minus Y1 is in S. So a convex combination of these 2 vectors is in S. Specifically, 1/2 times Y0 plus 1/2 times minus Y1 will be in S. And this is Q0. And this is minus Q1. So Q0 minus Q1 is in S. And it is also in the lattice. If there is a set S that is symmetric, convex, and with a volume that is strictly greater than 2 to the n times lambda, then there is a non-zero vector. In our case here, Q0 minus Q1, that is in S and also is in big lambda. Let's move to an application. We use Minkowski theorem to prove Lagrange's 4-square theorem, which states that every positive integer can be represented as the sum of 4 integer squares. And our focus will be P, which is an odd prime. Consider set S1, and this set S1 is generated by taking the integers from 0 to P minus 1 over 2, and then obtaining the squares mod B. So for example, if B is equal to 17, then we take X equal 0, 1, 2, all the way to 8. And then we compute the squares mod B. So we will get 0, 1, 4, 9, 16. Then we have 5 squared. 5 squared is 25. 25 mod 17 is equal to 8. And then we have 36. 36 mod 17 is 2, because 36 is 2 plus 17 times 2. So here we have 2, and so on. So we take those numbers, square them, mod P. How many values of X do we have? We have P plus 1 over 2 values for X, from 0 all the way to P minus 1 over 2. Now we show that the cardinality of the set S1 is also P plus 1 over 2, which means that the squares mod B that are generated are distinct. Suppose that x1 squared is congruent to x2 squared mod B. Then x1 squared minus x2 squared is congruent to 0 mod B. So this means that this difference of 2 squares, or this product x1 minus x2 times x1 plus x2, is divisible by P. Because P is a prime number, then B divides x1 minus x2, which is not the case. So B must divide x1 plus x2. x1 plus x2 is equal to B, because each x is in this range. But if their sum is equal to B, and each x is in this range, then the only possibility is that both x1 and x2 are equal, and both are equal to B minus 1 over 2. But x1 is not equal to x2. So if x1 and x2 are distinct, x1 squared and x2 squared are distinct, mod P. So the cardinality of set S1 is B plus 1 over 2. Set S2, here we take the numbers, again between 0 to B minus 1 over 2, but what we compute is not y squared mod B, but minus 1 minus y squared mod B. But using the same idea, if we have y1 not equal to y2 in this range, then if we equate, then we will find that we should have y1 squared is congruent to y2 squared mod b. But this will lead us that y1 is congruent to y2 mod b, but they are distinct. So again, those generated values will be distinct, and the cardinality of set S2 is also b plus 1 over 2. S1 is b plus 1 over 2 non-negative integers that are in this set from 0 all the way to b minus 1. Note that we compute mod b. S2 is the same, b plus 1 over 2 non-negative integers also from this set here from 0 all the way to b minus 1. This set contains b non-negative integers. The sum of the elements in these two sets is p plus 1. It must be the case that there is at least one element that is common between S1 and S2. Let's go back to our example. If p is equal to 17, S1 is equal to 0, 1, 4, 9, 16, 8, 2, 15, 13, and S2 is equal to 16, 15, 12, 7, 0, 8, 14, 1, and 3. 16 is here and there, 8 is here and there, and so on. In the general case, we are guaranteed to have one common element, again, because we have two sets. We contain numbers from this set of b non-negative integers from 0 to b minus 1, but the cardinality of each set is p plus 1 over 2. Because of this, there is alpha squared that is congruent to minus 1 minus beta squared mod b. There must exist alpha and beta such that alpha squared mod b is congruent to minus 1 minus beta squared mod b. This means that alpha squared plus beta squared plus 1, which can be written as 1 squared, and then we can put here 0 squared, is congruent to 0 mod p, which means that this alpha squared plus p squared plus 1 squared plus 0 squared is equal to a positive integer times p or 2p or 3p, and so on. This is not exactly what we want to show. We want to show that p itself can be written as the sum of 4 squares. Now we have a multiple of b that can be written as the sum. What about b itself? This is where we can employ Minkowski. Consider the lattice lambda, and lambda is represented by this 4 by 4 matrix B. And so the columns of B are B1, B2, B3, B4, and they are linearly independent. If you check this matrix, it is upper triangular, and the elements on the main diagonal are P, P1, 1. So the determinant is P squared, the product of the elements on the main diagonal, which is definitely not equal to 0. This matrix is invertible, and its columns are linearly independent. Note that the elements in the matrix are P, and then here in this submatrix, we have alpha and beta, and these are the numbers that are obtained from S1 and S2. How do the vectors in the lattice look like? What if we take B and multiply it by a vector of 4 integers? What if we construct an integer combination of the columns of matrix B? Then we will get this vector B1 times V1 plus this vector times V2 plus this vector times V3 plus this vector times V4. And this is the result that we get. Compute the L2 norm squared of this vector. So we will take each element and square. We have V3 squared plus V4 squared plus the square of this sum and the square of this sum, which can be expanded like this. If we take the L2 norm squared mod B, then all the terms that include P or P squared are congruent to 0 mod B, and we are left with V3 squared plus V4 squared times this bracket. These two guys appear multiplied by 1, like in these two terms. They appear multiplied by alpha squared. Here is V4 squared times alpha squared, and V3 squared times alpha squared, and they appear multiplied by beta squared. Here is beta squared V3 squared, and beta squared V4 squared. The remaining terms contain P or P squared, and then there are two terms that are free from P, but they appear with an opposite sign. If we take this L2 norm squared mod P, we get V3 squared plus V4 squared times this. But this bracket is 0 modulo P, which means that this L2 norm squared is congruent to 0 mod P. This sum is P or 2P or any positive integer times P. We are not sure that it is P. It is a positive integer multiple of P. Let's take a set here, C, and this set is a 4-dimensional ball. So this is the set x1 squared plus x2 squared plus x3 squared plus x4 squared is less than r squared. So these are the points whose distance to the origin of R4 is less than r. Note that the 4-dimensional ball is symmetric. if there is a point y in this set C, then minus y is also in the same set C. Also, it is a convex set. 2 points in this 4-dimensional ball, if you connect them, all the points on the line segment connecting any 2 points in the set are in the set itself. This set is symmetric, is convex, and now we want to choose the radius r such that we have the condition of Minkowski theorem. We want the volume of this set to be greater than 2 to the power n times lambda. N is 4. We are working in R4. And what is lambda? What is the volume of the fundamental cell? So there is a result in the study of lattices, which is that the volume of the fundamental cell is the magnitude of the determinant of B. In our case here, lambda will be p squared. We want the volume of C to be greater than 2 to the power n, which is 4, times lambda, which is p squared. We want the volume of C to be greater than 16b squared. What is the volume of n ball? So the volume of an n ball, so the general formula is that it is pi to the power n over 2 divided by gamma n over 2 plus 1. And then we have the radius raised to the power n. In our case, n is equal to 4. So this is pi squared divided by gamma. And then here we have 4 divided by 2. That's 2 plus 1, gamma 3. And gamma 3 is equal to the factorial of 2, which is 2. And then we have r to the power 4. So the volume is pi squared over 2 times r to the power 4. If we want to apply Minkowski, then we need to choose the radius such that pi squared over 2 r to the power 4 is strictly greater than 16b squared. From this, we find that r should be greater than this number times the square root of p, and this number is approximately 1.34. So we are good if we choose r to be 1.4 times the square root of p. If we choose this r, then we will satisfy the condition in Minkowski theorem. So what is the theorem telling us? It's telling us that there will be a point in this set C. The points in the set C are characterized by their distances to the origin being less than r. So that's the set C. There is a point in the set C which at the same time is a point in the lattice. And a point in the lattice means that it can be written as this matrix here times a vector containing 4 integers. By Minkowski, there must be a non-zero vector. Here this vector is not the all zero vector. And so this vector is in the lattice. This vector is also in C. So the L2 norm squared of this vector must be less than r squared by definition, by how C is defined. It's the 4-dimensional ball. So this L2 norm squared is less than r squared. Now we have chosen r to be 1.4 square root b, which is enough to apply Minkowski. So this r squared is 1.96 times b. This means that r squared is strictly less than 2b. But recall that the L2 norm squared modulo b is congruent to 0, which means that the L2 norm squared is p or 2b or 3b and so on. Now we are sure that there is a non-zero vector here such that b times that vector will be a point in the lattice, and this point has a distance squared from the origin that is less than 1.96 p. But this is p or 2b or 3b and so on. So the only possibility is that this L2 norm squared is exactly equal to b. There exist those 4 integers. They cannot all be 0 at the same time, such that the L2 norm squared, and what is the L2 norm squared? It's the sum of 4 squares, and this is equal to p. So indeed, the prime number p can be represented as the sum of 4 squares. So far, the result that we have is that any odd prime can be represented as the sum of the squares of 4 integers. The prime number 2 can be represented as 1 squared plus 1 squared plus 0 squared plus 0 squared. So all primes can be represented as the sum of 4 squares. What about the non-prime numbers? The idea is that if we have 2 numbers, each one of them is representable as the sum of 4 squares, then their product will also have the same property, which is it can be represented as the sum of 4 squares. If we take this as a number that is written as the sum of 4 squares, that's another number. And then what if we multiply them together? We will get a result. Interestingly, the result can be written as the sum of 4 squares. So we have this identity here, which can be checked by expanding both right and left hand sides and checking that they are exactly the same. Any integer n greater than 1 can be represented as a product of prime numbers. That's the fundamental theorem of arithmetic, or the prime factorization theorem. So n is, let's say, prime p1 to the power alpha 1, p2 to the power alpha 2, all the way to pk to the power alpha k. Now, each prime can be represented as the sum of 4 squares. And so any power of a prime using this property here can be represented as the sum of 4 squares. And this product is representable as the sum of 4 squares.